All right, think about it for a second. Your phone, your TV remote, your flashlight, they all run on batteries. They're kind of the unsung heroes of our daily lives, right? And they might seem simple, but inside every single one of them is this tiny, powerful engine. So let's crack one open, figuratively of course, and really see what makes them tick.
I mean, have you ever really wondered what's going on in there? When you plug in your laptop, where does that power actually go? Well, I'll tell you, it's not magic, it's pure, awesome chemistry.
Basically, every single battery is just this little self-contained box that turns chemical energy straight into electricity. You can almost think of it like a pocket-sized power plant. And you know what? We're about to pop the hood and see how it works. So this hidden engine we're talking about, it has a proper scientific name. It's called an electrochemical cell. And at the heart of it all is this really fundamental chemical process that's all about moving tiny little particles around.
And that process is called a redox reaction. It sounds complicated, but it's a really simple and powerful idea. All it means is that one chemical gives away electrons while another one grabs them. And there's a great little trick to remember this. Just think oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. It's that simple transfer, that little handoff, that creates the flow of electricity.
Okay, so we have this electron transfer, but how do we actually harness that to, power something? Well, we do it with a device called a galvanic cell. You might also hear it called a voltaic cell. The key thing to know about this one is that it spontaneously creates electricity. It just happens on its own.
And here we go. This is the classic setup right here. You can see you've got two separate containers, right? We call those half cells. Inside each one, there's an electrode. You see the zinc and the copper there sitting in a solution. And then see how they're connected? There's a wire up top for the electrons to travel through. And then that U-shaped thing in the middle, that's the salt bridge, and it's super important for keeping all the charges balanced. All right, to really get this, we need to meet our two main characters. First up, we have the electrode, where the electrons are lost, where the oxidation happens. We call that the anode. And on the other side, the electrode that gains the electrons, where reduction happens, that's the cathode. And hey, here are a couple of super easy ways to remember this forever. An-ox, anode is oxidation, and red cat, reduction happens at the cathode. You won't forget that now. So here's the play-by-play of what happens. First, over at the anode, the zinc starts to give up its electrons. Boom, they're released. Those electrons then zip right through that wire, and that flow is the electrical current. They race all the way over to the cathode, where they're eagerly snapped up by the copper ions in the solution. And all the while, that salt bridge is doing its job, letting ions move back and forth to make sure the charge doesn't build up and stop the whole show. And just like that, the circuit is complete, and bam, you've got power. Okay, but that whole process is about creating power. What if you wanted to do the opposite? What if you wanted to use electricity to force a chemical reaction to happen? Well, for that, you're going to need a totally different kind of engine. It's called the electrolytic cell. And the key word here really is force. A galvanic cell, that's a spontaneous reaction. It just happens, kind of like a ball rolling downhill. But an electrolytic cell, that's a non-spontaneous reaction. You have to push it. You need an external power source. Think of plugging something into a wall outlet to drive that reaction uphill. So instead of creating power, this one actually consumes it. And this chart here just lays out the differences perfectly. Look, galvanic cell, chemical to electrical energy. Electrolytic, the exact opposite, electrical to chemical. One spontaneous, the other is forced. But check out the bottom two rows, the polarity. In a galvanic cell, the anode is negative, but in an electrolytic cell, it's positive. That swap is a really, really important difference to keep in mind. So if we're going to boil it all down, here's the simplest way to think about it. A galvanic cell is like a ball rolling downhill. It just happens, and it releases energy. An electrolytic cell, that's you having to push that same ball all the way back up the hill. It takes work. You have to put energy in. All right, so we've covered all the theory: galvanic, electrolytic, uphill, downhill. Now, here's the big payoff. Because these two types of cells, they perfectly explain the difference between the two kinds of batteries you and I use every single day.
So on one hand, you've got primary batteries. These are your normal, single-use, throwaway batteries, like the AA is in your remote. Once the chemicals inside are spent, that's it, they're done. But then you have secondary batteries. And these are the rechargeable ones, the batteries in your phone, your laptop, even in electric cars.
So that disposable battery, it's just a galvanic cell. That's all it is. It's built for that one-way, downhill chemical reaction that just naturally creates electricity. And once it hits the bottom of that hill, well, game over. Its job is done.
Ah, but a rechargeable battery. This is where it all clicks into place. A rechargeable battery is this brilliant little piece of engineering that can actually be both.
And this right here is the magic trick. When you're using your phone, scrolling through social media or whatever, the battery is discharging, right? During that time, it's acting as a galvanic cell, spontaneously creating power. But then when you plug it into the wall, the charger forces electricity into it. Now it's switched modes. It's acting as an electrolytic cell, using that power to push the chemical reaction backwards, all the way back up the hill, getting it ready to go again.
Which, of course, leads to the one big question we all have. If we can just keep reversing the reaction, why don't rechargeable batteries last forever?
Yeah, why does your phone battery just seem to get worse and worse after a couple of years? Well, it turns out that even this super clever uphill-downhill process isn't perfect. Eventually, every single battery, whether it's rechargeable or not, hits the end of the line. And the ultimate cause of death for a battery is something called chemical equilibrium. See, over hundreds of charge cycles, little unwanted side reactions happen. Things get a little messy in there. And eventually, the main reaction just can't be reversed perfectly anymore. The battery gets to a point where there's no net flow of electrons. It's not that it's empty. It's just perfectly balanced. And for a battery, being balanced means it's dead.
So there you have it. We've looked under the hood of that hidden chemical engine. We've seen everything from that basic redox reaction all the way up to the complex two-way street inside your phone's battery. And as we demand more and more from our tech, from our phones to electric cars, the race is always on to build better, longer-lasting, and more powerful batteries. So the big question is, what's next? What will the next generation of this incredible hidden engine look like?